Welcome to qnawire.
Here, we've defined the velocity of a satellite going around Earth, given that we know its period in seconds. So first, let's start by rewriting our period in terms of v, the value we want to find. We know that t is equal to 2 pi over omega, and we can rewrite that as 2 pi r over v. All right, so that's good, but we don't know what r is. So let's use another set of equations to find that. We know that for a satellite moving around a planet, our centripetal force, mv squared over r, is going to be equal to our gravitational force, which is g times the mass of our satellite, little m, times the mass of our planet, me, over r squared. Now we can use this to solve for r, which is equal to me times g over v squared. Now that we have r in terms of v, we can plug it back in to our equation for t that we just found over here and solve for v. So let's rewrite we had earlier as v equals 2 pi r over t, which, as we just found, is 2 pi times me g. Oh, I realized that I switched between a big M and a little m. Let's keep that consistent. Me over g divided by, and so meg times 2 pi divided by t times v squared. Now we can simplify that, bring all our v's to the same side, and we get that v is going to be equal to the cube root of g times me times 2 pi all over our period. And those are all either constants or given quantities, so all that's left for us to do is plug in. G is our gravitational constant. It's kind of long, so I'm going to write it out down here instead. 6.67 times 10 to the negative 11 newtons times meters squared kilograms squared. And so it's going to be G times the mass of the Earth. That's 5.98 times 10 to the 24 kilograms times 2 pi. And that's all going to be over 1.20 times 10 to the 4th seconds. That is our period that we're given. And so, plugging that all into our calculator, we find that v is equal to 5.92 times 10 cubed meters per second, the solution to our problem.